Waduh, dokter gue ada juta kata. Okay, good morning. I waited for a few minutes because we still have 110 students. That means we are still short of 30 students. Not 30, roughly like 50 students. Anyway, I think now we can start. We should not wait or waste our time on those people. But anyway, I gave them a chance. Um, uh, so, am I audible to you all? Am I clear enough?
Yes.
Thank you. All right. We discussed some properties of derivatives. I introduced you derivatives last Monday, then discussed some properties of derivatives. Let me open my notes. We started talking about derivatives of special functions. Derivative of exponential functions, we discussed that part. Uh, I told you e to the power x is a very special function. Derivative of that function is the function itself. This is not the case with power functions, polynomial functions. We have some rules for differentiation now. We have the sum rule, constant multiple rule, product rule, quotient rule. So for with those functions, we can differentiate all the polynomial functions, rational functions. Then we increased our list of functions by discussing the derivative of exponential functions. And that is not the only special function. There are other special functions, logarithmic functions, for example. Um, Give me a second. So exponential function and logarithmic function, those are inverses of each other. So if we know the derivative of exponential function, there must be a way to find the derivative of its inverse function. Uh, Indeed, there is a nice way of finding it. Uh, for now, I will skip how we get this derivative, and I will show you the answer. So for us, derivative of the exponential function y equals e to the power x. E to the power x. The inverse function log of natural rates. Um, Unfortunately, the derivative of natural log of x is not natural log of x. There is a very special property that validates only for the exponential function. For natural log of x is 1 over x. Keep in mind that the natural log, the domain for natural log is all positive x values. Therefore, x not equal 0 applies automatically because 0 is not in the domain. So this gives us the derivative of natural log of x at any point. So if you think about the graph of natural log of x, log 1 is 0, and before that point, natural log is always positive, and after that, natural log is always negative. And according to the formula, as we increase x value, 1 over x decreases. So as we move forward along the graph, slope actually decreases. Function increases, but slope decreases. At this special point, at 1, comma 0. Here, derivative is 1. Slope of the tangent line is 1. But as we move forward, slope decreases. So the graph become more and more flat. On the other hand, as we go closer to 0, slope increases. Y-axis is a vertical asymptote. Y-axis is a vertical asymptote, so closer to y-axis, slope is enormously large. This is how the graph of natural log of x looks like. Now, you can combine natural log of x with other functions. Example, ln x plus e to the x minus 2x squared. So the derivative of this function, you can see this as a sum of three functions. And the sum rule applies for all three parts for the function. So natural log of x gives us 1 over x. E to the x is just e to the x minus. Now for this function, we can apply the constant multiple rule. So we keep minus 2 in front, differentiate x squared, which is 2x. So minus 4x. If you want, you can differentiate this one more time. 2y over dx2. For 1 over x, you can apply the power rule again, minus 1 times x to the minus 2. Again, e to the power x doesn't change, minus 4. So likewise, you can keep differentiating this if you want. And not only with the sum rule, you can combine the natural log with other functions using the product rule. For the second example, think of ln x plus x e to the 2 e to the power x plus 3. The product rule says if you differentiate something like u times v, this is u v prime plus u prime v. Now apply the product rule. This is our u, this is our v. So keep the first factor, differentiate the second factor, which is 2 times e to the x, plus, now differentiate the first factor, 1 over x plus 1, and keep the second factor. So in this way, you can differentiate functions with powers of x, natural log of x, and e to the power of x. Next, I want to discuss something about trigonometric functions. So far, we have been delaying this discussion. So trigonometric functions. So today I will discuss trigonometric functions in detail for you. So there are a few different trig functions. So all of these goes back to our desire to understand simple geometry. Let's say you have a simple right angle triangle. So say you have two of them. Let's say they, in addition to the right angle, they share the same angle. Then the remaining angle also the same because sum of all the angles of a triangle is 180 degrees, pi radians. So these are called similar triangles. Some are triangles with the same angles. In geometry, that's a theorem says for similar figures, not only for triangles, for similar other shapes, ratios between corresponding sides are equal. So because of this, you can say AB over AC equals A prime B prime over A prime C prime and likewise. And because of this, people realize that this ratio, it for a right triangle, the ratio does not depend on anything but the angle. So this depends only on the angle. So people came back to this triangle and give this ratio a name. So AB over AC. So since this depends only on the angle theta, they call this sine theta. Opposite opposite. This is the hypotenuse. This is the adjacent side for this angle theta. So they call this ratio the sine theta. Likewise, they gave a name for the adjacent side divided by hypotenuse. This is called the cosine theta. That also depends only on the angle theta. It does not depend on the size or the other angle. That's just purely a function of angle theta. Um, so we know some properties of these ratios. For example, we know some values. You may need to memorize these values because we need them for simple computations. So the first one is theta. Let me use radians. I suppose all of you are familiar with radians. So radian pi is 180 degrees. So 180 divided by 6 means 30 degrees. Then pi by 4, 45 degrees. then pi by 3, 60 degrees, pi by, yeah. So these are the simple angles that we can think of. Um, if the angle is 0, we will have a degenerate. So there will be no triangle. We'll have just a line segment. If you think about what happened as we decrease this angle to 0, you see there will be no and triangle. The same thing happens if you increase this angle theta to 90 degrees. Uh, at the end, the hypotenuse and this opposite side will be parallel to each other. There will be no triangle. It will be more closer to something like that. Something like that. If this is 90 degrees, this won't be a triangle anymore. So there are limiting cases, but if you think about if you guess what happened at those limiting cases, you can add those limiting cases into the same table. So let me give them a chance and add them to the table. So I will put here what happened if theta is 0, 30, 45, 60, and finally 90. So the first and last columns, they are actually not corresponding to any triangles, but those are limiting cases. What happened at the limit? At the limit, there will be no triangle, but we can sort of guess what happened. 0, 1, divide by 2, square root 2 divide by 2, square root 3 divide by 2. This is square root 4 divided by 2. This is 1. For cosine, we start from the last entry of the sine value and move forward. So you see, if you go forward from the sine row, that's same as going from the last entry to 4 backward along the cosine column. This is simply because in the triangle, if this angle is theta, the other angle is pi by 2 minus theta. So the opposite side of theta is really the adjacent side of this complementary angle. As a result, sine value of theta is equal to cosine value of the complementary angle. Cosine theta is same as the complementary value of sine. So complementary angle changes sine to cosine and cosine to sine. So cosine means complementary of sine, complementary value of sine of theta. Oh yeah, there's a typo. This should be pi by 3. Thank you. Right, so this is very good to know. Complementary of sine is cosine. Sine value of the complementary angle is cosine, and cosine value of the complementary angle is sine. So this is one of the relations between sine and cosine. Not only that, there are other relations. For example, The Pythagoras theorem says area of the squares drawn on these sides containing the right angle summed up to the area of the square drawn on the hypotenuse. If you divide both sides by AC, you get it simply says sine square plus cosine square theta equals 1. So square of the sine theta, usually we write it as sine square. But this square is just like sine theta. This is just a notation. So here is another relationship between sine and cosine. But when it comes to a right triangle, for a triangle to exist, theta must be a value between 0 and pi by 2. In fact, 0 and pi by 2 are not even in the domain of sine and cosine function at this point, but included them to get these limiting cases. So we force them to be in the domain. Those are not really natural numbers in the sense that we will not have triangles at those points. Anyway, so this sort of says sine and cosine are two functions, functions of angle theta, and theta vary from 0 to pi by 2. So later people wanted to extend this idea. So what they did was, instead of taking a right triangle, they took a circle. Right? So they took a circle, and they considered this angle theta. Take this point x and y. Let's say the radius of the circle is r, center is the origin. Now, if you remember our discussion on lines and Cartesian geometry, equation of this circle is just x square plus y square equals r square. Another application of the Pythagoras theorem. Now, this angle theta determines this point x comma y. Now, to connect this with trigonometry, we can consider this right triangle. So, according to the right triangle, sine theta is opposite divided by hypotenuse. Opposite side is this side, and that height is just the right coordinate. Cosine theta is adjacent divided by hypotenuse. For simplicity, some people choose this circle to be the unit circle. circle with radius 1. In that, for the unit circle, uh, sine theta is just the y coordinate. Y divided by 1 is just 1. And cosine theta is just the x coordinate. Once we made this choice, uh, we can actually define, extend this idea of sine and cosine values for angles other than angles in the range outside of this interval of 0 to pi by 2. For example, let's say I want to talk about the sine and cosine of angle of 120 degrees. So that means 2 pi by 3. Now, I can draw this unit circle. Go to the point on the circle corresponding to this angle and say sine theta, sorry, sine 2 pi by 3 is this y coordinate. Is this x coordinate. If you want, we can find the formulas for that. For example, let me complete this green color triangle. This angle over here is 30 degrees, pi by 6. And hypotenuse is 1. And since we know the trig function values, trigonometric values for pi by 6, opposite side is hypotenuse times, hypotenuse is r equals 1, sine pi by 6. Sine 30 is 1/2. Then adjacent side of that green color triangle is r cosine theta, sorry, cosine pi by 6. Cosine 30 is square root 3 divided by 2. So because of that, this opposite side is 1/2. This adjacent side is square root 3 divided by 2. Now, x coordinate is negative 1/2. Y coordinate is square root 3 divided by 2. So likewise, we can compute these trig function values for angles bigger than 90 degrees. And also in trigonometry, we have this convention of negative angles. We say angle measured in counterclockwise direction are positive, and angle measured in clockwise direction are negative. So because of that, For the same angle, we can have different names. Imagine this point over here. We know that point has 90 degrees. If you go in this direction. If we go in the negative direction, this is our minus pi by 2. This is minus pi, and on the other hand, this is minus 3 pi by 2. We keep going in the negative direction, this point will be minus 2 pi. Yeah, there is no restriction that we need to stop at some point. You can keep going circles around the origin. So pi by 2, if you go to the positive direction, pi by 2, that's pi. This is 3 pi by 2. This is 2 pi, which is also the 0. So the same point, for the same point, we have different names. So if you have the same, like two different names for the same angle, this angle over here, that is called the coterminal angle. Coterminal, like pi by 2 and minus 3 pi by 2. They are coterminal angles because they terminate at the same point. So they have the same ending point. 3 pi by 2 and minus 3 pi by 2 are also coterminal angles. For any angle theta, if you add a full circle, like 2 pi, that's the same angle. Or if you, let's say you're here, theta, if you go a full circle and come back to this point, it's 2 pi plus theta, but it is 2 pi if you travel in the positive direction. But if you travel in the negative direction and complete a full circle, that will be minus 2 pi plus theta. Or if you go 2 circles, 4 pi plus theta. So for any angle, theta, coterminal angles looks like multiples of 2 pi plus theta. Here n can be positive or negative integer. So these are coterminal angles. Coterminal angles because they have the same terminal point. And when they have the same coterminal angle, they share the same x and y coordinate. They share the same x and y coordinate. Therefore, they have the same sine and cosine values. For them, sine and cosine values are equal. Sine theta is always the opposite side. For unit circle, it is y. For cosine theta, it is x. Now on the unit circle, at this topmost point, y coordinate is 1, x coordinate is 0. At this rightmost point, x coordinate is 1, y coordinate is 0. At the bottom point, y equals -1, x is 0. and this leftmost point, x equals -1, y equals c2. So you can easily see the sine and cosine values for those angles. 0, 0 and all its coterminal angles, pi by 2 and all the coterminal angles, then this is pi and all its coterminal angles, and the bottom point is 3 pi by 2, 390-degree angles, and all the coterminal values of that. So we can usually easily memorize these values. Sometimes they are helpful. So with this unit circle definition, now we can think of sine and cosine as functions of theta. And the limit for theta is now, limit for theta has no bounds at this point. It can be any positive value or any negative value. Negative means we are traveling traveling clockwise. Positive means we are traveling clockwise. If theta value is bigger than 2 pi, that means we have completed more than a single circle. If somebody says theta equals 300 degrees, that means 60 shorter than 2 pi, that means somewhere here. So likewise, now theta has no bounds. Theta can be any real number. So theta can be any real number. Right? And in different quadrants, for example, in the first quadrant, both x and y coordinates are positive. In the second quadrant, x coordinate is negative, y coordinate is positive. In third quadrant, both x and y are negative. In fourth quadrant, x coordinate is positive, y coordinate is negative. So, as a result of this, in the first quadrant, both sine and cosine are positive. Maybe I should say all, both or all. Then in the second quadrant, x coordinate is negative. That means cosine values must be negative, but the y coordinate is positive. Y means sine theta. In third quadrant, both are negative. In fourth quadrant, cosine is positive. Both are negative in the third quadrant. Right? So this is how sign change, algebraic sign changes across different quadrants. So far we discussed only about sine and cosine functions. And in addition to sine and cosine values, in calculations we see sine cosine function, a lot of their combinations. Sometimes they are quotient, sometimes they are reciprocals. So as you see something repeatedly, it is better to introduce a symbol for that. So people realize this, especially for astronomical computations, for navigations. When the early mathematicians made computations, they encountered sine, cosine, and all their calculations. So to make their computations easier, they introduced other trigonometric functions. You already know these. Tan theta. Tan theta is sine theta divided by cosine theta. Sine and cosine are the primary trig functions, but these are tan theta and other functions are secondary. So in terms of the unit circle, sine theta divided by cosine theta is y divided by x. We need to make sure x is non-zero. If it is zero, we will have a problem. For example, x is zero here and here. So for those 2 points, we will not have a meaningful assignment. For example, if somebody asks you the value of tangent pi by 2, at this point x coordinate is 0, therefore tan theta has no meaning, because the definition breaks down, it fails. Tan theta has no value at all. So tan pi by 2 is a meaningless thing. Tan 90 degrees is a meaningless thing. Then 1 over sine theta. We call this cosec theta. Or some people write it as CSC. Because usually we use 3 letters to write down a trig function. So if you follow that convention, this should be CSC. But sometimes we expel it out a little bit and say cosec theta. And sec theta is 1 over cosine theta. So these reciprocal functions also have their limits. Some of them are defined only when x is non-zero, and some defines only when y is non-zero. And there is another function, cot, means 1 over tan. That means cosine theta divided by sine theta. So we have introduced tan theta, cosec theta, sec theta, and cot theta. Cot means complementary of tangent, so they are complementary to each other. So that means tan of 90 minus theta will be cot theta. Cot 90 minus theta will be tan theta. Likewise, secant and cosecant are complementary trig functions. So sine, cosine, tan, cotangent, secant, cosecant, they are complementary pairs. And if you go back to this picture of sign changes, in the third quadrant, both sine and cosine are negative, their quotient tan theta will be positive. So this is how you should memorize this circle. There is a phrase that you can use to memorize this. All student take cal. All student takes calculus. Or some people say South African cricket team. Whatever um, you can use any phrase that is convenient for you. But anyhow, you should memorize this. So sine, cosine, uh, and their variance. Uh, right. Do you have any questions? So I sort of went through all these basic stuff about your trigonometry within 1 hour. This is not that much. What we did was we started from the trigonometry, like right triangle definition of trig functions. Then I extended it using a circle. So because of this reason, sometimes people use the term circular functions or trigonometric functions. They are no longer called trigonometric functions because now there is a relation between these functions and circles, not only a relation between trig functions and trigonometric triangles. So circular functions. And then we can compute other trigonometric ratios using other trigonometric values using um, the known trig function values and the sign conventions. For example, let's say somebody wants you to compute cotangent of 300 degrees. Say somebody wants you to find cotangent 300. How can you do that? If you want, you can first convert 300 into radians. So this single radian is pi divided by 180 degrees. Then 6 times 5, 6 times 3. So the answer is 5 by 3. Now let's go and draw a Cartesian plane. $300 means 60 shorter than a full circle. This is pi by 3. And we know about the pi by 3. Pi by 3 is 60 degrees. For a 60-degree triangle, when the hypotenuse is 1, opposite side is 1/2, sine pi by 3 is square root 3 divided by 2. Cosine pi by 3 is 1/2, so adjacent side is 1/2. Now, for cotan, so of pi by 3, we know cotangent is cosine divided by sine. Cosine divided by sine. So cosine means the x-coordinate. X-coordinate is positive 1/2 divided by sine. So adjacent. Let me write it. X divided by 1. Let me make sure. Yeah, x divided by 1. X coordinate is positive 1/2 divided by y coordinate is now negative. Negative square root 3 divided by 2. So negative 1 over square root 3. Negative 1 over square root 3. Now, even at this point, these complementary relations like sine pi by 2 minus theta equals cosine theta. Cosine pi by 2 minus theta equals sine theta. All these things are still valid, even in this range. And more importantly, we still have this Pythagoras relation to trig function values. You can take this last relation and convert it to relations between other trig functions. For example, if you take this identity and divide whole thing by, let's say, cosine theta, so sine theta divided by cosine theta square plus cosine theta divided by cosine theta square was 1 divided by cosine theta square. We took the Pythagoras identity and divided everything by cosine square. Now this is simply tan square theta plus 1 equals secant square theta. Likewise, if you divided everything by sine theta, you will get uh, one plus cotangent square equals cosec square theta. Those are also uh, considered as Pythagorean identities for trig function values. Uh, all right. Mm, do you have any questions? Do you have any questions about trig function values or trigonometric functions in general? Anything? Is everything clear so far? Do not hesitate to ask questions. Type it in the chat or turn on your mic and ask. Umindo wants to see the computations of cotangent 300. Right? All right. Since there are no more questions, I'll discuss one last topic. We know so sine and cosine are two functions. If you think about this relation, this function, y equals sine x. So you can ask for the graph of this function. Sine theta values are always bounded between 1 and -1. Remember, x coordinate, sorry, sine theta is the y coordinate, and y coordinate always vary between -1 and 1 on the circle. On the circle, y coordinate is always change in this range. The bottom point is 0, -1, and top point is 0, 1. So y values are always between 0 and 1. As a result, sine values are always 1 and always between 1 and -1. When x is 0, sine theta is 0. When x is pi by 2, sine theta is 1. Then when is pi, x is pi, sine theta is again 0. Three pi at 3 pi by 2 is minus 1 and 2 pi is again 0. So the graph of sine function goes something like the wave. This is called a sinusoidal curve. This is a perfect picture to model waves. The cosine function is somewhat similar, but now it goes something like this. That is y equals cosine theta. There is a phase difference between them. The difference is 90 degrees. So you take the graph of sine function and translate it by pi by 2 units. Mm, Next, we talk about addition formulas. We know sine of, let's say, sum of two angles. Like any other function, this cannot be sine A plus sine B. It can be, but we need a justification for that. We know functions usually do not work in this fashion. We know x plus y square. The square function does not work in this way. Or we know e to the x plus y is completely different from e to the x plus e to the y. Functions usually does not work in this fashion. The correct formula is not sine A plus sine B. It is sine A cosine B plus cosine A sine B. There is a similar formula for cosines. Cosine A plus B. This is cosine A cosine B minus sine A sine B. These are not that important for our discussion. You really need a basic understanding of trig functions, which I think you have now. Now, the sine and cosine functions are important to understand uh, periodic phenomena. Periodic phenomena. We'll come back to this topic later. But for now, Our main discussion is about derivatives. Now that we know about sine and cosine as functions, I will tell you about their derivatives. If y equals sine x, the derivative of sine function is cosine x. Very simple. But this is a little bit different for cosine function. Derivative of cosine x is not sine x. It's not sine x. It is minus sine x. This sign change is really important. Minus sine x. So you need to make sure memorize this pretty clearly. For sine, just cosine x. For cosine, it is minus sine x. Now we can actually compute the derivatives of other two functions using quotient and product rules. For example, let's say y equals tan theta. This is sine divided by cosine. For the derivative, now we need to use the quotient rule. Remember, for u divided by v u prime minus u v prime divided by v square. So cosine is derivative of sine is again cosine minus sine x derivative of cosine is minus sine x. Divided by cosine square. So this is cosine square x plus sine square divided by cosine square. Cosine square plus sine square is 1. 1 divided by cosine is secant. So secant square x. Derivative of tan is secant square. Let's go to our notes. Rules. For the basic trig function, sine and cosine we know, and this is enough actually to talk about derivatives of all these types of trig functions. These two are enough. We'll skip this. We don't need this derivation. We don't need to know the reason for this value. Now let's keep it aside. Let's talk about some examples. So find the derivative of cosine x plus 5xy minus sine x. I will give you 2 minutes for this. Let's practice this. Since we know the derivative of cosine and all these power functions, we should be able to do this very quickly. So now it is 10 past 20. I can give you 2 minutes for this. Right. Very good. Almost all of you got it correct. Derivative of sine is derivative of cosine is minus sine x, and derivative of 5xy is 10x, and derivative of negative 7x is negative 7. Now we can combine this new knowledge of derivative of sine and cosine with product and quotient rules. For example, let's say x square sine x, product of two functions. The first factor is x square, the second factor is sine x. Then you can apply the product rule. Keep x square, differentiate sine, plus keep sine and differentiate x square. So x square cosine x plus 2x times sine x. The same goes with all these type of products, quotients, and since we can compute the derivative of other trig functions using the quotient rule and derivative of sine and cosine, we can make a table of them. Derivative of sine is cosine, for cosine minus sine x, for tan it is secant square, for cotangent minus secant, cosecant square, for secant, secant times tangent, for cosecant minus cosecant times cotangent. You don't need to memorize this table. If you can memorize it, it's great, but you don't necessarily need to memorize it. You can construct it. Whenever you want the derivative of, let's say, secant, think of it as 1 over cosine and apply the quotient rule. Mm, So these notes are already in the LMS, so you can go there and practice these problems. We already talked about exponentials and log functions. Now you can think of combination of powers, exponentials, log, and trig functions. All these things, now you can differentiate. Not only those individual functions, they are products, quotients. Right? So we still have a little bit of a problem because now we can differentiate summation of functions, product of functions, quotients of functions. But these are not the only ways to combine functions. There is a special way to combine functions called compositions. We can compose functions, but so far we do not have an obvious way of differentiating two composition of two functions. Say, let's say we have f of x equals x square, g of x equals sine x. Then, so in this case, f is the outer function, x square. So sine square x. We can differentiate this function by thinking of this as sine times sine and applying the product rule. So this function is okay for us, but the other composition, this looks a little bit scary. So outer function is g, inner function is f. sine x square. How can we differentiate this function? This is not a product because this is not the product between sine and x square. This is, you have inside sine function you have x square. So this is not the product, not a quotient, not a summation, none of those. So we need a rule to differentiate something like this. So here is how we do it. If you have something like this, to differentiate this function, we start from the outer function. The outer function is g, and f is the inner function. Hmm? So we start from the outer function. So g is the outer function, differentiate it, but do not do anything to the inner function f. So differentiate outer function without looking at the inner function. Then once you're done with the outer function, forget about it. Move inside and differentiate the inner function. That's how we differentiate it. For example, sine x squared. The outer function is sine. So to differentiate it, start from the outer function. Differentiate sine. Derivative of sine is cosine. Don't do anything to the inner function once we are done with the outer function. So we differentiated the outer function. Now we are done with it. Forget about it. Go inside, differentiate the inner function. Multiply it. This is how we differentiate a composition of functions. Not only this function, think about a chain of compositions. Right? Sine of e to the power of 2x plus 3. Here we have composition of three functions. The outermost function is sine, then the middle function is exponential function, and the innermost function is 2x plus 3. Composition of three functions. Again, the differentiation works in the same way. Differentiate the outer function. Don't do anything to inside. Once you are done with sine function, forget about it. Go to the next function, differentiate it. That is the exponential function. Exponential function doesn't care about differentiation. It stays like it is. Now we are done with the exponential function. Go even further, and it's 2x plus 3 there. Differentiate that. As a linear function, derivative is 2. So this is the derivative of this composition. This is called the chain rule because like in a chain, you differentiate the one link, do not worry about the others. So once we are done with it, move to the next link, differentiate it, then move to the next link, differentiate it until you are done with all these linked, all these functions. You start from the outermost function and keep differentiating and come to inside. I want you to differentiate this function. Think about this. Take your time. Okay, I got some answers and let's see. Um, so the first thing to notice is this is really a composition of two functions. The outer function is power one half, and inside that we have some other function. So to differentiate this function, first of all, we need to differentiate the outer function. Power one half means it is a power function. So the way we differentiate power function is bring the exponent to front, reduce the current exponent by 1. Don't do anything to the inner part. So this is how we differentiate the outer function, the power function. Now then move on to the inside, differentiate the inside. Derivative of x squared is 2x plus derivative of tan. This is something we learned today. It is secant square. Yeah, that's it. So if you simplify it a little bit, you can make it to 2 times x squared plus tan x. That's it. Uh, Next, let's look at the notes. Chain rule. Already I introduced you the chain rule. Chain rule is how we differentiate composition of two functions. So let's read what it says. The chain rule and composite functions. The chain rule deals with composite functions and added a surprising versatility to the rules previously introduced. So previously we knew how to differentiate sums, products, quotients, uh, power functions, trigonometric functions, exponential and log functions. And once we discuss the chain rule, that increased our capability by a huge amount. With this, we can differentiate any function. Uh, so without chain rule, we could differentiate these left-hand side functions. X squared plus 1, cosine x, 3x plus 5, x plus secant x. Now look at the right-hand side. Square root of x squared plus 1, cosine of 3x, 3x plus 5 to the power 4, x plus secant of x squared. So these right hand functions are really complicated compared to their counterpart in the left hand side. But with the chain rule, we can differentiate all these functions in the right hand side. Um, Decomposing composite functions. Yeah, let's look at these functions in the uh, slide and try to see them as composite functions. The first example is 1 over x plus 1. That is a composite function, composition of two functions. The outermost function is the reciprocal, 1 over x. Inside that we have x plus 1. So x plus 1 is the inner function. Then for b, it is clear that the outer function is sine and inner function is 2x. For 3, we can easily see the outer function is square root of x, and the inner function is 3x squared minus x minus 1. Uh, So given a composition function, you should be able to recognize this. What is the outer function? What is the inner function? If there are many parts, you need to understand them or you need to recognize them in order. To differentiate a composition, uh, we first identify the outer function and inner function. Then we differentiate the outermost function while keeping the inner function. Then we differentiate. Then we forget about the outer function. The outer function does not participate in the second term. We differentiate the inner function. Look at this. 3x to the fourth power minus 6 plus 2 raised to the seventh power. Seventh power is the outer function, outermost function. And inner function is 3x square minus 6 plus 2. So to differentiate this, we first differentiate the outer function. Keep the inner part as it is, differentiate the outer function. Bring the exponent to front, reduce the exponent by 1 unit. Then differentiate the inner function. Derivative of 3x to the fourth power is 12x to the third, then minus 1 plus 0. Third example. Let me write it in the notepad. Okay. 5 3x to the fourth power minus 6 plus 2 raised to power 2. If you want, you can differentiate this using the quotient rule. It is not wrong, but it is a little bit involved. So I will think of this as a power function. Now it has this outer function and inner function. Now it is more like a composition. Now this 5 in front is not a problem. I can think of it as a constant. So this is a function multiplied by a constant. So I can apply the constant multiple rule. I will keep it in front and do not worry about it. I bring the exponent to front and differentiate the outer function. And then I will differentiate the inner function. You see, this chain rule approach is much quicker compared to applying the quotient rule. But if you want, you can apply the quotient rule separately and see whether you get the same answer. Maybe you should do that, and that way you can check your ability to apply these different rules. My notes are very detailed, but when you have more details, sometimes you get confused. So just look at this last line. And just look at the last line and see whether you can understand the answer. Something like sine applied to x squared is much simpler You differentiate the outer function while keeping the inner part, then you differentiate the inner part. The same rule applies when you have functions made by more than two composition functions made by more than two components. Let me see whether I have something like that. Think about this. E to the sine x squared divided by x plus 1. When you have three functions, let's differentiate them. The order, the outer function is exponential and it does nothing. Because the derivative of e to the x is itself. Then let's differentiate sine. Derivative of sine is cosine. And you still keep the inner part of sine function. Now we are done with e and sine, and then go even further and apply the quotient rule. So the denominator is x plus 1, its derivative is 2x minus the other bit, x squared, derivative of x plus 1 is 1 divided by x plus 1 squared. So once we simplify it is either sine x squared plus x squared over x plus 1 cosine x squared over x plus 1. Now if you would simplify this, that will be 2x minus x squared divided by x plus 1 squared. That's it. So calculus is really the way we deal with functions. So next time we'll discuss a few more techniques to differentiate these complicated functions. Please go through the remaining notes 3.3, 3.4, and 3.5. All right. We'll meet again tomorrow.